Hi, I'm Rakshita from CSE AML Section C. My topic is photonic crystal structures with tunable structure color as colorimetric sensors. Let's get into the topic. Photonic crystal color cycle. Photonic crystals are optical nanostructures with a periodic change in diffractive index that affect the propagation of light, similar to how atomic lattices affect electron conductivity. The process begins with inspired Boeing's by design and leads to the creation of photonic crystals which can then be used to generate structural colors. These structural colors are created by the interference and diffraction of visible light by the periodic nano or microstructures of the crystals rather than by synthetic dyes. The cycle continues with the ability to enable colorimetric sensings and achieve dynamic tunability, which refers to the ability to change the color of the crystals. Applications of the technology include color displays, sensors, and anti-counterfeiting measures. Photonic crystals are optical nanometers with a periodic changes in refractive index that affect the propagation of light, similar to how atomic lattices affect electronic conductivity. Structural colors in photonic crystals. It represents a diagram shows how different properties contribute to the final visual output. The outcome is color perception, the final visual outcome of structural color. Instant angle is creates iridescence and viewing effects. Wavelength describes determines the perce- perceived color. Lattice spacing describes affects the color spectrum through swelling. Refractive index describes modifies the color via analyte interaction. Tuning mechanisms. Mechanisms which outlines different ways to change the properties of materials, particularly polymers. Swelling or striking. Polymers change size based on their environment. Stretching alters structure, changing colors. This refers to mechanical deformation that changes a material's optical properties. Analyte binding. Molecular recognition alters diffraction index. The mechanism involves a material's properties changing when it binds to a specific molecule. Analyte binding. Molecular recognition alters refractive index. External fields. Fields reorient particles inducing transitions. This describes how an external force like an electric or magnetic field can change the orientation of particles within a material, leading to a change in its properties. Colorimetric sensing applications. Chemical detection. Molecularity imprinted polymers change color from blue to red when they bind to retractline with a detection limit of 0.37 nanometers. Biomedical sensing. Stretchable 3D photonic crystals called as PCS are used to identify saccharides with rainbow-like color shifts for glucose detection in point-of-care devices. Environmental monitoring. Humidity sensors are PCs which higher order photonic bands to shift colors from green to red in response to humidity levels between 30 to 95% RH. Mechanical sensing. Mechanochromic fibers which combine colloidal pieces with spandex shift color from red to blue when stretched, making them useful for wearable monitors. Stimulus response performance comparison. The table compares four types of photonic crystals: inverse opal, hydrogel, PNI, PAM, embedded colloidal, elastomeric 3D PC, and MIP DC PC. The stimuli begin tested are pH, temperature, pressure or strain, and biomolecules. Each PC type shows a specific color shift in response to its corresponding stimulus. The applications listed include food spoilage, monitoring, thermochromic labels, structural health monitoring, and point of care diagnostics. Chemical detections, molecularity, imprinted polymers change color from blue to red when they bind to tetracycline with a detection limit of 0.37 nanometer. Biomedical sensing. Stretchable 3D photonic crystal species are used to identify saccharides with rainbow-like color shifts for glucose detection in point-of-care devices. Synergy of structural color and sensing technologies. Structural color dynamics. That involves light nanostructure interaction. Sensing technologies. These use detection and mastering methods. Advanced detective solutions. This is achieved through the synergy of structural color and sensing technologies, enabling enhanced real-time monitoring. Phonetic crystals are materials with a periodic arrangement of materials that have different refractive indices. They bend light differently. The periodic structure causes certain wavelength colors of light to be reflected with while others pass through, similar to how a crystal diffracts X-rays. Because of this, photonic crystals can produce structural color that comes not from pigments, but from light interferences and reflection. Structural color. Structural color arises from a interaction of light with nanostructures. The color depends on the period of the crystal layers, the refraction index contrast, the viewing angle. Example of this nature. Peacock feathers or butterfly wings show brilliant colors due to photonic crystal effects. Tunable structural color. Tunable means the color can change in response to external stimuli. In photonic crystal sensors, the spacing between layers or the refractive index can change due to temperature, humidity, pH value, mechanical strain, chemical binding. These changes alter how light is reflected, shifting the color. Example from blue to green, green to red. Working principle as colorimetric sensors. Photonic crystal structures can be used as colorimetric sensors, meaning they detect changes by color. No electrical equipment needed. Mechanisms. The photonic crystal has a periodic spacing d. When exposed to an analyte, gas, liquid, chemical, the spacing or refractive index changes. This causes a shift in the reflective wavelength, lambda, according to Bragg's law, and equals to 2 nd sine theta. N defines about refractive index, D defines about lattice spacing, theta is defines about incident angle. Advantages of this: no need for complex instruments, visual color readout, high sensitivity to small changes, can be miniaturized and portable, biocompatibility, useful in biosensing. Photonic crystal collaborative sensors use tunable structures, color, to detect environmental or chemical changes. Their operation is based on light interferences in a periodic nanostructure where any change in structure or refractive index alters the reflected wavelength, leading to a visible color shift that signals detection. Thank you.